thank everybody for your time today. We really appreciate your interest and spending time with us today in regards to our today's topic. Today's topic is Wi-Fi 6E. I'm saying gigabit Wi-Fi. So we'll as we go through this this presentation, this webinar, we'll discuss more about Wi-Fi 6E and how it operates, how it performs. But is it really gigabit Wi-Fi? Can you use it now? That's the question, really. I think for a lot of folks, should I be installing this now? You know, our new Wi-Fi 6E will access point will come out the beginning of June. So for you, again, for anybody joining today, I'm going to be brave, and I'm going to. This webinar's being broadcasted across 6 gigahertz through our ECW 336, which is a Wi-Fi 6E access point. It's a tri-band access point. We'll talk more about that, but I am broadcasting this webinar on that particular AP. I just showed everybody my Wi-Fi connection. It's operating on 6 gigahertz. I'm in, I can't remember the channel. I think it's 197. I'm operating on the higher channel within 6 gigahertz. I am running 6 gigahertz at my house right now on this particular access point just to test. So we'll let's dive right into it. We're at 3 minutes past the hour now. So what my agenda is today is to talk about Wi-Fi 6 or just Wi-Fi just in general, and to talk about the history a little bit and how we got to Wi-Fi 6. Then we'll talk about what is Wi-Fi 6E. You know, you just talked about Wi-Fi 6. What is Wi-Fi 6E? What are the benefits of Wi-Fi 6E? And what is EnGenius offering for a Wi-Fi 6E solution? So we'll talk about that, and then we'll open it up for any Q&A. Now, these topics I'll talk at a high level. I won't try to get into the weeds. We'll try to answer any questions that you might have, but we might have to come back and answer these questions later, just to give you a heads up on that. But we'll try to answer as much as you can about that. So again, I appreciate your time, and let's get right into this. So let's talk about Wi-Fi 6. As a review, this is where we are today. I think any projects that you're installing today should be on Wi-Fi 6. It should not be on Wi-Fi 5, which is 11AC. I think you should be installing Wi-Fi 6, regardless of the ISP speeds. If, you know, I've had customers tell me my ISP speed is only 50 megabits, I won't be able to utilize Wi-Fi 6. That's not true. Wi-Fi 6, it's just way more efficient. The end user or the client device that's on that network will see benefit in communicating on Wi-Fi 6 rather than on older technology like Wi-Fi 5. It's just more efficient, and we'll talk a little more about that. So let's quickly talk about the different generations of Wi-Fi 5. Eddie and myself, and I believe Peter is in the same boat. We've been in this industry since the beginning of Wi-Fi. 802.11a, I'll start right at the top. And 802.11b, they were introduced in 1999. 11a operated on 5 gigahertz, or does operate on 5 gigahertz. 802.11b operates on 2.4 gigahertz. The major difference, obviously, is the band that operates on, the frequency band, but also the speeds that you could see from communicating on those frequencies. 11A would provide up to 54 megabits per second, and 11B would broadcast around 11 megabits per second, or up to 11 megabits and up to 54 megabits per second. 11B was adopted way faster than 11A. In fact, and I believe that's the early adoption of different technologies or by different companies. It was just way more cost effective to operate on 11B. You know, if you remember that generation, we were operating on PCMCIA cards, mini PCI cards, and then we even got into USB. One of our first bridges was an Ethernet bridge. It was an indoor Ethernet bridge, which the WISP market started to really use. It was operating on 11B, and we were seeing, I think we were seeing 2 megabits per second, which was actually pretty fast at the time because we're doing it wirelessly. We're not running cable at all. So it was such a huge relief to connect buildings on 11B and be able to communicate and share networks across buildings and so on. So the chase that we've gone through these generations of Wi-Fi is we want to be as fast as wired speeds. That was one thing. The other thing was the security side of things. That's always been a part of Wi-Fi as well, like the speeds and security of those things. So you'll see as we go through the different versions, and you're probably already really aware the speeds continuously climb. Security is getting better and better and better. But that was in 99. 802.11g was introduced in 2003. That operates on 2.4 gigahertz. That provided up to 54 megabits per second, which was very similar to 11A, going up to 54 megabits per second. This was a pretty big leap to be able to achieve those speeds on 2.4 gigahertz. We were quickly starting to run out of channels in 2.4. There's only 3 non-overlapping channels within 2.4, which I think a lot of you already are aware of. 1, 6, and 11. I think even my mom probably knows that by now. But we're running out of channels quickly with 2.4 gigahertz. So, the question was always, when are we going to move to 5 gigahertz? And so 802.11 was introduced in 2009. And that technology operated on 2.4 gigahertz and 5 gigahertz. That provided up to 600 megabits per second. These are aggregate speeds. It provided the ability to communicate on 2.4 and 5 gigahertz, but also the adoption of 5 gigahertz really started to take place again at this point. It was not reinvented, but reintroduced to a lot of the manufacturers that were out there. Manufacturers both on the wireless router side, the access point side, along with the client side, client adapters, and so on. So 802.11n was introduced in 2009, and then in 2013, doesn't seem very long ago, 802.11ac was introduced. That came in 2 waves, wave 1 and wave 2. Pretty much everything that is being manufactured on 802.11ac right now is wave 2. If you're using 11ac, I hope you're on wave 2. So that became available on 5 gigahertz. So you see the trend that, we're starting to move to 5 gigahertz because you have more channels and you have more non-overlapping channels within 5 gigahertz. And so that was the beauty of that. So everybody started to understand from 2009 that we needed to get on 5 gigahertz quickly because the networks and Wi-Fi was being utilized so much that 2.4 was overcrowded. Let's move to 5 gigahertz or use both bands and be able to maximize on these bands together. And 5 gigahertz, the technology just got better in regards to 11ac, and you had up to 1.3 gigabits per second. So, and that's theoretical speeds that we're talking about, maximum speeds provided. They're all theoretical. I know everybody loves talking about theoretical speeds, but that's what they were. And then more recently in 2019, 11ax was introduced both on 2.4 gigahertz and 5 gigahertz. You kind of see the trend there. When we are making transitions, we like to go to both bands and be able to operate on both bands. But this is a huge deal to be able to operate on 2.4 and 5 gigahertz with this newest and greatest technology of 11ax. And that was up to 10 gigabit per second. I think that's aggregate speeds it's referencing, but also theoretical speeds. We saw major improvements with 11ax. Just the communication was way more efficient. We'll talk about the benefits of 11ax. But as I mentioned before, you should be definitely deploying. It doesn't matter if it's a low density or a high density network. You should be deploying 11ax. The Wi-Fi Alliance came in and basically renamed these items, these versions, to simplify things. And you'll see this on the next slide. 802.11b is Wi-Fi 1, 11a is 2, G is 3, N is 4, AC is 5, and AX is Wi-Fi 6. So myself, Eddie, and Peter have been working within these frequency ranges for the longest time. We've installed thousands, hundreds of thousands of networks with this technology. So when we start talking about Wi-Fi 6E, it's mind-boggling to me to see how much more space we can work in, and we'll talk more about that. That brings us to today, Wi-Fi 6, which is 802.11ax. And here are the Wi-Fi standards: Wi-Fi 1, 2, 3, 4, 5, and 6. There's a lot of benefits with 802.11ax and how it communicates wirelessly, namely OFDMA. OFDMA really, which is one benefit of Wi-Fi 6, probably one of the biggest benefits of Wi-Fi 6. I don't know, maybe there's a CWNE that would maybe object to that, but I think that is probably one of the most important pieces, but they all work together, obviously. OFDMA enables more efficient channel use. It reduces latency between APs and client devices, and it also provides backwards compatibility with 2.4 and 5 gigahertz. So I do want you to keep in mind that when we talk about these benefits, we're still talking about operating on 2.4 and 5 gigahertz. So these are all these benefits, right? 1024 QAM was also a major benefit. This really boosts the throughput by 25% and provides really greater reliability and shorter distances in regards to like 5 gigahertz. Just to give you kind of an idea, and I think a lot of us have tested Wi-Fi 6, you can achieve probably around 800 spikes of 800 megabits per second with a really good connection, say in a 2x2 client device to like a 4x4 access point. You could see on average like 600 megabits, maybe even a little bit higher. We've had customers and or reviewers do our access point, which performed really well. They were seeing even highs like 800 megabits per second. So the speeds were pretty great with Wi-Fi 6, operating in 5 gigahertz, operating at 80 megahertz wide channels, right? So, but they'll vary depending on environment, obviously. Target wait time was another benefit. That really reduces power consumption. It allows the AP to communicate with the client devices. It can schedule wake times and extends client battery life of mobile and IoT devices. So that was really a major improvement with Wi-Fi 6. Another item is BSS coloring and spatial reuse. BSS coloring really tags packets with a color, and that's to help differentiate between adjacent service sets or other broadcast names. Spatial reuse enables simultaneous transmissions on the same channel via the BSS coloring, excuse me. So another benefit. Another benefit was uplink and downlink of multi-user MIMO. That supports up to, I think it's 8. It was 8 and 11 AC that carried over to Wi-Fi 6 or 11AX. Supports up to 8 client devices and provides greater network efficiency. Also focuses the radio energy on specific users and ensures optimal signal and reception reliability with those particular users. So you have up to 8. So in a small scale kind of network, that is really beneficial in like a small office. In larger offices, you're really more dependent on the OFDMA side of things. Another thing that is not talked about too much, but longer OFDM symbols. This really enables shorter wait times between data transmissions, and it tolerates more noise, which allows greater coverage. So this really helps in the outdoor space. Whereas if you're using the ECW 260 access point, which is a Wi-Fi 6 access point, you'll see benefits in there. We have a lot of folks that use the ECW 260, which is an outdoor rated access point, Wi-Fi 6, 2.4 and 5 gigahertz in warehouses. We see this application a lot for this particular device, but a longer OFDM symbols help in scenarios like that. It allows you to actually put up the to mount the access point up a little bit higher as well. So these are some of the benefits of Wi-Fi 6 or 802.11ax, and you'll understand why I wanted to talk about this first before we venture into Wi-Fi 6E. But these are the current benefits. This is what you're going to see with the devices that are available today when you're deploying our Wi-Fi 6 access points indoor and outdoor. I didn't do a deep dive into these individual items. There's more items that we could talk about, but I want to give you a high level of, okay, where's the history of this solution and where we're at today. In regards to Wi-Fi 6, we've had a lot of successes. These advanced Wi-Fi 6 features give us better performance and larger and higher profile installations. EnGenius and more importantly, our partners have been able to serve high profile and high density applications such as the Davis Cup. We worked with a private college, St. Thomas, more recently college, in Wi-Fi 6, and even early on in Taiwan, Taipei, we deployed Wi-Fi 6 at a New Year's Eve celebration utilizing the efficiency and performance of Wi-Fi 6. Just to give you an idea, the Davis Cup, there was about 12,000 attendees at that particular event. We used the ECW 230, I believe, in that application. At the college, there's probably about 2,000 plus students and staff. We also use the ECW 230. These are 4x4 Wi-Fi 6 access points. Those networks, all those client devices are really operating on 5 gigahertz, just to give you an idea. We had hundreds of people at a diving championship that used Wi-Fi 6. And at the Taipei New Year's celebration, there's approximately 20,000 attendees, along with the event staff that communicated on these devices, and they were also operating on the ECW 230 device. So 4x4 Wi-Fi 6 solution. It can be used pretty much anywhere, high density, low density. We come out with a price point that's competitive enough that you could probably put it into your house. So Wi-Fi 6 has been a great success for us so far, and we continue to push Wi-Fi 6. And that's the way to go if you're doing new installs. So what is Wi-Fi 6E? So this brings us up to this point. We talked about Wi-Fi 6. So Wi-Fi 6E is an extension of Wi-Fi 6. So it's an extension of Wi-Fi 6. All that technology we just talked about at a high level can apply to Wi-Fi 6E. So the combination of the higher efficiency wireless protocol in a super wide frequency band like Wi-Fi 6E is going to be, I say, and I think a lot of other folks are saying, a game changer for the Wi-Fi industry. It really puts us in a new arena. To give you a little insight into Wi-Fi 6E, early 2020, the FCC made 1,200 megahertz of spectrum available for unlicensed band and 6 gigahertz. As you know, 2.4 and 5 gigahertz are unlicensed. Now we're adding 6 gigahertz to the unlicensed band. 6 gigahertz spectrum offers double the channels that 2.4 offers and 5 gigahertz offers combined. So 6 gigahertz spectrum offers double the channels that 2.4 and 5 gigahertz offers. Late 2020, the Wi-Fi Alliance quickly got involved and announced Wi-Fi 6E as an extension to Wi-Fi 6. So 6 gigahertz devices will use Wi-Fi 6 or 802.11ax technology to operate in this band. So the laptop I'm running on right now is operating on the 210AX, or excuse me, the 210 Intel 210 wireless card. It operates on 2.4, 5 gigahertz, and 6 gigahertz. It's communicating on 6 gigahertz using 802.11ax on the 6 gigahertz band, just to give you an understanding of that or what that means. Let's see, let me just check my tabs really quick here. Okay, so that leads us to Wi-Fi 6E. So it's free free unlicensed 6 gigahertz channel that it basically triples the Wi-Fi spectrum. So now we're using what? 2.4, 5 gigahertz, 6 gigahertz now. So Wi-Fi 6E will really help alleviate problems of network congestion and solves the challenges related to crowded environments, small environments to very, very large environments. It's going to improve the responsiveness of cloud and collaboration applications, and it will allow teams to really enjoy faster speeds when sharing, backing up, and updating files. So there's huge potential here, and we'll talk more about this. It will also support larger bandwidth loads, process faster multi-gigabit data, achieves low latency, provides reliable and secure connections. Any Wi-Fi 6E device, it will utilize WPA3 to communicate on this band, unless you're introducing an older device that's but actually no, I apologize, correction. When you're operating on 6 gigahertz, the security type is going to be WPA3, the wireless security, so the most secure. Wi-Fi 6E will help us meet any demands for larger bandwidth, things such as real-time mass transmissions required by like augmented reality, virtual reality, and metaverse applications. So the one thing I really want to highlight here is that between the 3 bands, when you look at 6 gigahertz, we've spent 22 years within these 2 frequency bands. We've deployed, EnGenius has deployed hundreds of thousands of networks in these technologies, in these frequencies. Now they're opening up 6 gigahertz. Look how large 6 gigahertz. More importantly, look at the channel counts at the bottom here. For 20 megahertz, you have about 60 channels versus 25 and 3. In 40 megahertz, you have 29 versus 12 and 1. And in 80 megahertz, you have 14 versus 6 and really no 80 megahertz and 2.4. And then in 160 megahertz, you have 7 within 6 gigahertz versus only 2 in 5 gigahertz. So you may or may not be aware, the more access points you implement or install into a application, you have to be really careful about the channels that you use and how wide the channels that you select. And this is in reference to that. This is the number of channels and the width of the channels that you're using. So in today's networks, typically in a home environment where it's rural, you're typically, you can get away with using 80 megahertz. If you're lucky, you might be able to use 160 megahertz if the technology is built within the router and within your client device. You can use that, but typically in a residential space, because it's rural, there's no interference or very little interference, you can get away with 80 megahertz. I live in Los Angeles. I'm actually using 80 megahertz at my house, and it operates fine. There's really no interference with that in that scenario. But you will never find a case in a business, a small business, where you're going to use 80 megahertz or even 40 megahertz. I know in our office we have 5 access points. We cover about 10,000 square feet. We're operating on 40 megahertz. 80 megahertz is just too wide. It brings in a lot of noise when you bond channels together. You don't have a lot of channels. When you start bonding channels together, you don't have a lot of channels to choose from. So you get co-channel interference as well. So we're in 40 megahertz. In the large deployments of Wi-Fi 6 on 5 gigahertz, we're typically at 40 megahertz and even 20 megahertz. 20 megahertz makes more sense when you have a lot of access points. You have less co-channel interference, and you have more channels to choose from if you're statically configuring access points. So one of the cases I'm thinking of, we have about 600 access points deployed. They're all operating on 5 gigahertz. All the client devices are on 5 gigahertz. We're operating at 20 megahertz for those particular situations. We have 25 non-overlapping channels or channels to choose from within that arena. When you go into 6 gigahertz, you have a larger channel selection, and you can use wider channels. So in the case of a 10,000 square foot office and with 5 access points, I could potentially get away with 160 megahertz. When you broaden your channels like that, or you bond channels that way, the speeds dramatically climb or go and improve. But you do have to be cautious of your SNR or your signal noise ratio for your devices. But the FCC has implemented it and has added something into communicating on 6 gigahertz to help offset the noise floor in these scenarios. So we'll help improve the noise levels that increase when you bond channels. But just to give you an idea, in our office, we could operate on 160 megahertz pretty easily, so we can see the benefits of the wider channels. If we wanted to move to 80 megahertz, which is unheard of in today's networks, you would not use 80 megahertz in a 5 AP deployment. And so you could actually utilize 80 megahertz in this office, if not 160 megahertz. In a crowded area, you probably get away with 80 or 40. So that's a major improvement on the width of the channel in itself. The other thing that I'd like to bring up, let me back up one more. Sorry, I wanted to talk about one more thing about 2.4, 5, and 6. When you look at 2.4 gigahertz, 5 gigahertz, and 6 gigahertz in regards to the wavelength, as we all know it, 2.4 gigahertz will travel really, really far. It penetrates through more obstacles, and it travels greater. I think a lot of us already know that. 5 gigahertz, the wavelength is shorter. So it doesn't travel as far, and it doesn't penetrate through obstacles like walls, for example, as well. To give you an idea, 5 gigahertz, the wavelength is about 2 inches, just over 2 inches. That's the wavelength. And so in today's world, and the way we design networks are around 5 gigahertz because all the client devices that we're operating with are operating on 5 gigahertz. The reason we're doing that is because you can achieve faster speeds on 5 gigahertz. Thus, the client device will have a better experience. So we design all of our networks around 5 gigahertz. So the coverage area is based around 5 gigahertz. The number of access points that are deployed, the overlapping of the devices are considered when putting in 5 gigahertz. The reason I bring this up and I talk about this is because when you look at the 6 gigahertz wavelength, it's just at about 2 inches. It's just below 2 inches, the wavelength. So what I'm telling you is that the range of 6 gigahertz is not that far off from 5 gigahertz. So a lot of the networks that you've deployed when designing around 5 gigahertz is going to be somewhat similar to 6 gigahertz. I guess we will see, but it should be very, very similar. The range that we're seeing on our access points is pretty similar. So operating on 6 gigahertz, having a clear or less interference, faster speeds potential is definitely there, and so it should give you about the same coverage. Just to give you an idea of what the capabilities are with Wi-Fi 6E. So let's talk about the benefits. I've pretty much talked to them on more of a technical level. There's more information out there if you want to do deep dives into the individual items that, the benefits of what Wi-Fi 6E will bring. But it will definitely bring greater capacity. Like I said, the 6 gigahertz spectrum is more than double the 2.4 and 5 gigahertz spectrum, boosting 7 brand new 160 megahertz wide channels. If you're doing a lot of residential, you could put those individuals on 160 megahertz. The caveat to that is obviously they need to be operating on the client side on 6 gigahertz. You just have to keep that in mind. It's more efficient to operate on 6 gigahertz. That 6 gigahertz traffic will benefit from the spectrum management and efficiencies of Wi-Fi 6. It will be free from interference from basically 2 decades of legacy devices on 2.4 and 5 gigahertz. So you're clear of that when you're operating on 6 gigahertz. Definitely get higher performance where you see multi-gigabit speeds and ultra-low latencies. I think you will. And this will be perfect for gaming, like I said before, augmented virtual reality. When you have customers that are working in like robotics, for example, and other latency sensitive applications, 6 gigahertz is going to be the way to go. So let's talk about, can you use 6 gigahertz today? So the client adoption is really growing. I want to say the client adoption for 6 gigahertz is, I think, trending higher than it is for Wi-Fi 6 just in general. Today, pretty much every client device, any new client device is operating on 6 gigahertz, or not 6, Wi-Fi 6. So that the trend is rapidly growing, moving to 6 gigahertz. So nearly 20% of the Wi-Fi 6 devices shipped are expected to support 6 gigahertz by 2022. The global Wi-Fi 6 and Wi-Fi 6E chipset market is estimated to reach about 43 billion by 2028. So you can see the growth is very, very large. More than 338 million Wi-Fi 6E devices are expected to enter the market in 2021. So this is data that you can simply pull, but you can see that the trends are rapidly growing. Right now, the client devices that are out there that I'm aware of, and maybe you're aware of some, and you can put them in the chat if you'd like. There's Dell laptops, Lenovo laptops that support 6 gigahertz. The Samsung Galaxy S21 also supports 6 gigahertz. The Google Pixel 6 and Pixel Pro support 6 gigahertz. And then I mentioned it at the beginning, the Intel AX210, which you can buy offline, or excuse me, online, is about $35, $35 to $50. I've seen it. You can buy that, and you can put that into your older laptop. I've had customers use the AX210 or the Intel AX210 in an older laptop with the same antennas. You can buy them with antennas or buy them without antennas, but if you buy them with antennas, you have to replace your antennas in your laptop. But I do have a customer that bought them without the antennas and attached them to their old antennas, and it worked really well, actually. So you could get away with doing that. I would probably suggest buying them with the antennas, just to be on the safe side. My laptop, which is a Lenovo, I'm operating on the Intel AX210. I'm communicating or broadcasting across 6 gigahertz. So the adoption is definitely there. So I think there is a case for client devices coming on board. In September, we should see if the newest iPhone will support 6 gigahertz. If anybody is aware of it will support it, drop that in the chat if you don't mind. And then the other benefit to 6 gigahertz is access point to access point communication. So meshing on 6 gigahertz band could be a very major benefit. Currently, if you're meshing on 6 gigahertz, you're operating on a clear and not interfered frequency band. So high bandwidth backhaul connections are capable within this realm. So as I mentioned before, the distances of 6 gigahertz it's pretty similar to 5 gigahertz. So if you're already meshing on 5 gigahertz, you could pretty much take those APs, swap them out for new APs operating on 6 gigahertz and mesh on them, and then broadcast your SSIDs on 2.4 and 5 gigahertz. So all your legacy access points, or excuse me, all your legacy client devices that can only communicate on 5 or 2.4 can still communicate to an access point and then backhaul across 6 gigahertz. And now you have faster backhaul links between your access points. So this is another use case for 6 gigahertz. So client devices are adopting very quickly. The other method would be backhauling or meshing on 6 gigahertz. This would be 2 scenarios I would look at. So yeah, I think there is a case for 6 gigahertz, definitely on the meshing side. And in our office, we're starting to see the adoption of 6E on the client side. So that's my input on that particular case. I don't know, Eddie, if you want to comment on that, or Peter, if you want to comment on that at all.
I'm good. All right.
Same here.
Okay, perfect. So let's talk about EnGenius's solution, the Wi-Fi 6E product line that we have available. So the ECW 336, I'm actually performing this webinar. If you didn't hear me early on, I'm performing this webinar wirelessly using the ECW 336. Let me see if I can share that info really quick again. Yeah. So here's just to give you an idea, I'm operating on a test access point. We're using 11AX. I'm using WPA3 Personal for this particular case. My card is the Intel AX210. It's 160 megahertz. That's really important to know. The network band I'm operating on is 6. Let's not look at my MAC address. It's probably too late for that, but that's okay. 6 gigahertz. I'm operating on the network channels 197. I was operating on a lower channel previously, but I changed it to 197. My link speed or my connection speed was 2.1 gigabit by 1.1 gigabit. And I think the wired speed on this particular network that we're testing on was 150. Hopefully you can see my screen. Yeah, so I'm seeing about 120. This is testing out to the internet, so just to give you an idea. We'll let that go. So the ECW 336, it's a Wi-Fi 6E tri-band access point. MSRP will be $699, so it will operate on 2.4, 5 gigahertz, and 6 gigahertz. We're a manufacturer, so we manufacture our products. We have direct relationships with Qualcomm. We're using the Qualcomm quad-core CPU. On 2.4, theoretical is 1.1 gigabit. 5 gigahertz is 2.4 gigabit, and 6 gigahertz is 4.8 gigabit. This particular design is a 4x4 antenna design. That's a 4x4 on 2.4, 5, and 6. The Ethernet port is a 5 gigabit Ethernet. It's PoE plus, so it's 802.3 AT compliant. So it will work with any PoE injector that's standardized, any PoE switch that's standardized. It will work. It will work best on an EnGenius switch. That's kind of a joke, but then the radio power is 23 dBm on the 2.4 and 5 and 6 gigahertz radios. The dBi gain of the antenna, the 2.4 is 5, 5 is 6, and 6 gigahertz is 5. This is an FCC, CE, and IC compliant device. This access point is has a 2-year warranty. This is a cloud managed access point. Just to give you an idea of that. And the one other thing I wanted to quickly show is, let me just do this really quick. Maybe I'll show that later. Okay. Okay, so let's talk about some of the lab testing we've done so far with the ECW 336. And Peter and I think Eddie can comment on some of the testing that we've performed. So with the Intel AX210, the Samsung S21, and then the EnGenius ECW 336 in mesh mode. The Intel is a 2x2, the Samsung's a 2x2, and this access point is a 4x4. So you have to keep those items in mind. These are the bands that we tested on, 5 gigahertz, 6 gigahertz, across all three client devices. The reason I'm just talking about these three is because the channel width is on 80 megahertz, and the transmit power, or excuse me, transmit speeds and receive speeds are here at the end. So you can see on a 2x2, the Intel, we saw about 800 megabits per second when operating on 6 gigahertz and 80 megahertz, about 900 to about 900. I feel comfortable saying 900 megabits per second. On the Samsung, saw actually higher speeds, 80 megahertz on 5 gigahertz. We saw about 900, 910, somewhere around there. On 6 gigahertz, we saw about 920. So a slight gain there. This is 80 megahertz. And you could, in today's network environments and residential spaces, and even small offices, you can get away with 80 megahertz, no problem. So you can have multiple devices connected at 80 megahertz. When you're communicating from a 4x4 to another 4x4, these I should say, and I apologize, I didn't say this, these client devices are communicating to the ECW 336 in access point mode. In this test, we're testing a ECW 336 in meshing mode to another ECW 336, which is a 4x4 to 4x4 communication on 5 gigahertz and 6 on 80 megahertz. About 1.6 gigabit was the average. On 6 gigahertz, 2.1 gigabits. That speed is tremendous. So imagine a backhaul, mesh backhaul, communicating that quickly. Now, obviously, the ranges you're going to want to understand, and also the environment. Obviously, you have to look at the SNR and things like that. Okay, the bottom three, we're talking about the same scenarios, same antenna designs, but now we're talking about 160 megahertz. Look at the differences when you move to 160 megahertz. So as I mentioned, in this office, it's about 10,000 square foot office. We have 5 access points. All of those access points could be on 160 megahertz. And so we could easily have client devices communicating on 160 megahertz if they're all 6 gigabit or 6 gigahertz. So 1.5 or 1.4, somewhere around there on the Intel, almost 1.7 on the 6 gigahertz, 1.4 on the Samsung, 1.7 or 1.6, somewhere around there on the Samsung. And then when in mesh mode, 1.6 on 5 gigahertz, and then 3 gigabit on 6 gigahertz in mesh mode. So really great throughput speeds that we're seeing. This is at short distances. When we did field testing, and I think this is where Peter can really chime in, and or Eddie. Our field test, we tested the 336. It was connected to our multi-gig switch, which is the ECS 2528. It's a 24-port multi-gig. The PC was running Windows 11. The Wi-Fi card was AX210, the one that we talked about. It's like a $35 to $50 cost. I think on Amazon, you can even buy them on eBay. We're operating on 160 megahertz. We're using channel 5, bonded channels, 1 through 29, so channel 5. And the transmit power was set to auto. The security set was WPA3, which is the most secure Wi-Fi security, minus like enterprise. Client speed link was 2.4 gigabits. Actual speeds ranged anywhere from 1.2 to 1.4 gigabits per second. So Peter, can you comment a little bit further on that anything I missed on that in regards to your testing? Can you talk about the range testing that you did, or if you tested through multiple walls?
Definitely. So hello everybody. So we did some testings in different scenarios. The first one was actually we did it outside. I was able to put this access point on a tripod, and I wanted to have clean line of sight to see if there were any differences when it came to distance. So I was able to go all the way to 90 feet away from the access point, and the connection was pretty stable. We kept achieving around the 1.1 to the 1.4 gigabit speeds. Something to mention about is the computers that I used. Actually, I had two of them, two client devices that I upgraded their card. If you're updating a laptop, just make sure that it has an M.2 connector, and it should support it. And then if you're doing a desktop, we also have a PCIe expansion card, and that one is also running the Wi-Fi 6E. So those are the two clients that we used to do those testings on iPerf. And as Brian mentioned, those were the speeds that we did achieve.
Hey, thanks, Peter. That was great information in regards to just in general, but specifically about the card and the connector types of those particular client cards. The other thing I would mention is that if you're running Windows 10, there is a blog out there where you have to modify the registry, so you have to do a regedit for it to operate on Windows 10. This laptop that I'm operating on came with Windows 10. I didn't want to do the regedit, which I think is pretty basic for a majority of people to do. I just updated to Windows 11, and sure enough, Windows 11 I was able to connect and test from there. So just another note in addition to that. So if you are running Windows 10, you either have to do a regedit or you have to update to Windows 11. Eddie, anything that you would add to that, or?
Yeah. So Wi-Fi 6E, as Brian mentioned, right, the high throughput, and also Peter showed you the test result, right? So since Wi-Fi 6E is a new spectrum, right, being available, before, if you ask me and Brian, say, hey, should I use 80 megahertz on the 11AC wave 2? Maybe my answer or Brian's answer will say no, because you will get a lot of interference. So for Wi-Fi 6E, even using 160 megahertz wide channel will become reality as the new wider spectrum, provide adequate channel to decide wireless network. So 6 gigahertz, one thing I want to highlight, the standard, this 6 gigahertz standard does not limit the transmit power on the AP as the channel with increase. So, the AP can continue to use the same transmit power irrespectively, of the channel with this config on the AP itself. And Brian also mentioned about the reduction in interference, right? So this 6 gigahertz has a large number of the channel, it can available for Wi-Fi 6E and AP, and as well as the client to use. So this reduce interference in the wireless network. So that's why you can see that the test result Peter was conduct, and is extremely high test result, right? So in addition to high throughput and reduction in interference, just want to add some comment, and also Brian mentioned about the security, right? So with Wi-Fi 6E, WPA3 will be mandatory along the management frame protection. So this kind of help, increase the security. And also, the first thing Brian mentioned is additional capacity, right? Because Wi-Fi 6E, we have a ECW336, we have tri-band, 2.4, 5, and 6 gigahertz. So it provide the wireless connectivity to the client device on those 3 bands simultaneously. So kind of increase the overall capacity of the wireless network in terms of serving client device, So yeah, Brian, that's something I want to just highlight. And yeah, You can
Yeah,
continue.
perfect. No, that's great. Thank you so much for that. That both Peter and Eddie, if you haven't worked with them, hopefully you have the opportunity to work with them. Provide a lot of great information in regards to our technologies just in general. So the one thing I'm showing on my screen is, in cloud, you can see the client activity and live clients. One of the things I really wanted to highlight is that, I'm operating on 6 gigahertz. This is a misread right now because we're doing some fine tuning on cloud, but my SNR is about 28. It just changed. It went from like 30 to 28. So it's the RSSI is negative 62. My link speed or my download speed is actually 164. So this is my laptop. So you can see the SNR is really good. Anything above an SNR of 25 or greater is considered a good signal quality, and an SNR of 10 or lower is considered very low. So I'm operating on 160 megahertz on 6 gigahertz, and my SNR is really, really good. So I just want to share that with you really quick.